In this video, we're going to start our work in section 12.4 on linear functions. So you've seen linear functions before when we've looked at graphs of one variable, which, as we've seen, are represented on a two-dimensional plane. So here's a graph. A linear function in one variable input looks like a line. So I'll just maybe write that down. So in 2D, two dimensions, this is a line, or a linear function looks like f of x equals mx plus b, if you'd like. All right, so now in this chapter, we're working with two variables, so functions where we have two inputs. So let's look at the definition of such a object of a linear function with two inputs. So we see a definition. So a function, and this actually definition is more general, but we're just looking at when our output is equal to the function value where we have two inputs, an x and a y. So this function is called linear if it has a constant slope in each direction. The graph of a linear function is a plane in three-dimensional space. So a linear function of one variable is a line. With two variable inputs, we get a plane. So let's make a little bit more sense of what it means to have a constant slope in each direction. So I'm just going to look at some points on this plane that were given in this diagram on our page. So let's just label a couple points. So I'll look at a point here, P. So from P, I can take I can go along my plane in various directions. So when we mean in each direction, by direction, we mean a straight line intuitively on the surface. So for example, here's one direction we could approach, and I'm actually going to use my shape drawer to really make sure that's straight. So here's one direction we could go. I'm going to go down to say, let's point Q. And I could have another point here that I'm labeling R, and we could have a direction or a line between them. So we can see that no matter where you go on your plane, if you take these straight lines, you get constant slopes along these lines. All right, so let's think about some other things that we can observe about planes using the image that we have here. Okay, so one question that I'll ask you is, if you were to climb up this plane, starting at Q or R, which path to get to P would be the steepest? And the reason why I'm asking this is because in thinking about this problem, we're thinking about the slope of our plane along these various lines. So take a moment, pause the video, and think about that question. Which approach from Q to P or R to P is steepest? All right, so now let's think about it together. Well, one way to think about it is that if you start at Q or R and you go to P, imagine this was a mountain, you're going to be climbing up in the same distance. So you're going to go an elevation of a certain amount, no matter which point you start with, Q or R. But we can see that the distance from Q to P is going to be less than the distance from P to R, because we're like taking the hypotenuse, so to speak, of a little right triangle here. So this means that the approach from Q to P must be steeper because we're going along the plane. We're walking less, but we're going just as high. So let's go ahead and write that down. And you might have another way of describing that, and that's totally cool. All right, observation. So we could say that our climb is steepest or steeper along R to P than, let's rewrite that, Q to P, because again, we're going less distance along the plane, but we're getting the same height. So that means we're going to have to climb, kind of get higher for each step that we take. So it's steepest along this curve, and I'll just highlight it so that I don't write it in the wrong way again. So along Q to P, then R to P. And you might think about maybe an experience where you've been on a hike in a mountain and you've noticed, okay, here's my mountain, that some of the trails will have switchbacks. So why do you think that is? I'm not going to give it away. I'll just have you think about that. Why do we have switchbacks on steep mountains? All right, so now what's another observation we can make? Well, along any of these directions, we see that the slope of our approach is constant throughout. So if we go here, we're going to go up the same amount of over for any time or any location on this path. So the slopes stay constant along each straight path. So I'm going to write that down. The slope stays constant along each straight path. And this property here that we're observing, that's how we are defining what a linear function is that we have this same or constant slope in any direction. All right, so now let's look at what an equation of a linear function in two variables looks like. So we can look at this box together. It says if a plane, i.e. a linear function that's equal to z equals f of xy, has a slope of m in the x direction. So if we held y fixed and just changed, or held, y fixed and changed x, and a slope of n in the y direction, and passes through a point x naught, y naught, z naught, then the equation is given by the following formula. So that equation looks like, I'll write it down and then we'll look at it together. Z naught, so that z coordinate that we know is on our plane, plus m times x minus x naught, plus n times y minus y naught. So does this look familiar? So we can see that we're kind of seeing that equation of a line in two dimensions in this formula. So recall that that point slope form for a line looks like y minus y naught equals m times x minus x naught. So here recall x naught, y naught is a point on line, and m is slope of line. So again, this is called the point slope form of a line. So notice we can do what we can do with this formula. Well, if we add y naught to both sides, then we get y is equal to y naught plus m times x minus x naught. And we see that has a very similar form to that equation of a line that we were just working with here. All right, so in this section, we're going to get some more practice working with these lines, or rather planes, because we are in 3 dimensions. And we'll have an opportunity to get more comfortable working with them.